Good morning. My name is Samir Arya. I'm one of the 11 grandchildren of Professor Bal Mokand Anand. I'm speaking to you from Austin, Texas, USA. I'm also the son of Dr. Sharda Arya, who is a Ph.D. graduate in physics from Panjab University. I'm here to represent the Anand family. I really wish I could be in Chandigarh in person today. However, I have a family obligation. The Anand family would like to extend our warmest thank you to Vice Chancellor Dr. Renu Vij, the esteemed guest for the President.
Hello.
हेलो ठीक है इसको ऑफ कर दो निकालना हाँ
Hello.
और उनका खराब हो जाए तो इसको बस ऐसे घुमाने में
Hello.
अभी ऑफ कर दो ऐसे कोई वायर ना तीसरे नंबर पे इसको ऐसे हेलो ठीक है बस ठीक है होगा बोल देंगे ना जब प्रोफेसर आनंद होगा बोलेंगे ना उनके पास प्रोफेसर सर मुझे पता है जो बोलते हैं हम अंदर से पता है हाँ बुके तुमने इकट्ठे नहीं किए सर चलो वो पढ़ो किसी फ्रेंड के पास तुम लोग वहाँ वहीं खड़े रहना उनको पकड़ाने ये समझते हैं ना कहाँ तक चलाएंगे प्रोफेसर अरुण बोले के बाद गरीमा यूज करते रहते हैं
कुछ भी नहीं है ये क्लिक करना है मैं सिर्फ बता रहा हूँ अगर कोई दिक्कत जाती है चल पड़ी यहाँ से बोल चल पड़ी है ये
ठीक है जब मैं अभी सब आएंगे यही करना सर वो ना Good morning. On behalf of the chairperson and faculty of the Department of Physics, I welcome you all for the 7th B.M. Anand, Professor B.M. Anand Memorial Lecture and Book Launch event. Before we start the event, I request you all to please stand up for the PU anthem.
पंजाब विश्वविद्यालय तेरी शानो शौकत सदा रहे, मन में तेरा आदर मान और मोहब्बत सदा रहे। पंजाब विश्वविद्यालय तेरी शानो शौकत सदा रहे। तू है अपना भविष्य विधाता, पंख बिना परवान सिखाता, जीवन पुस्तक रोज पढ़ाकर सही गलत की समझ बढ़ाता।
जीवन पुस्तक रोज पढ़ाकर सही गलत की समझ बढ़ाता।
तेरी जय गौ शंख बजाए,
रोशन तारे बन जाए,
बखरी तेरी शोहरत सदा सदा रहे। पंजाब विश्वविद्यालय तेरी शानो शौकत सदा रहे। पंजाब विश्वविद्यालय तेरी शानो शौकत सदा रहे।
तमसो मा ज्योतिर्गमय, तमसो मा ज्योतिर्गमय।
Thank you. Now to begin the program, I request the chief guest of the function, Professor Harsh Nayyar, Director Research, respected ex-Vice Chancellors of Panjab University, Professors K.N. Pathak and Professor A.K. Grover, the dignitaries Professor Rajinder Singh, Professor S.M. Yusuf, and the Chairman, Department of Physics, Professor R.K. Puri, to please come on the stage for lamp lighting.
ये बांध रहा ना
So now I request Professor Puri to please hand over a bouquet to Professor Harsh Nair. देखिए करके देखिए Thank you. Before we start the book release function, I request Professor Rajiv Puri, Chairman, Department of Physics, to please come here and present a few opening remarks.
Thank you, Bhushan. Thank you, Bhushan. Professor Harsh Nair, Chief Guest, dignitary on the dais, my colleagues and students. This is a great honor for us to host the book release as well as the lecture on B.M. Anand Memorial Lecture. I am supposed to tell few things about the department. I think that today there will be good amount of history of the department. So if I see back in the pages, it was something like 1934 that this department started in Lahore, and then having a journey from Lahore to Hoshiarpur, then Delhi, and finally we landed here in 1958. The year of 1958 is very interesting in the history. If we see the Google Guru, what we find that US Congress started NASA in the year 1958. We are older by a couple of weeks than NASA. If you looked at anti-gravity dancer Michael Jackson, also born in 1958. If you are interested in food, Pizza Hut also started in 1958. If you look back at home, Dhirubhai Ambani started famous Reliance in 1958. Our defense sector, DRDO, started in 1958. Interestingly, Indian Parliament adopted the first science policy in 1958. So I think that we justify our shifting in 1958 as well. As far as department is concerned, we have a fleet of courses that includes doctoral courses, BSc, MSc courses. We have on the average 100 plus students for the Ph.D, 450 students for the BSc and MSc. Apart from that, we have a teaching strength of 20 plus. There was a time when we have 44 teachers in our kitty, but now the strength has reduced. But we are pumping in with the guest faculties, the postdoctorate. So I think that by large, our scholars, they are working for the three fields, the particle, solid and nuclear. And they are publishing good papers that you can see everywhere. So at the end, I again welcome everyone, and I hope that it will be interesting and informative lecture. Thank you very much.
Thank you, sir. Now I request all present here to please release the book. Thank you so much. I now invite Professor Rajinder Singh, author of this book, to please come on the dais and apprise the audience here about the book.
So, I am really not prepared because I was not told I have to say something. What I would like to say is a little bit about the book. I have written 43 books. Most of them, they deal with the Indian scientists. Some of them with the Nobel Prizes, and some on the science education, because from profession I'm a science teacher, I'm a physicist, and I'm also a trained historian of science. So that is why it is possible for me to interconnect different fields. Writing the biography of a person when the family is living, children are still alive, grandchildren, colleagues, students, it is quite complicated story. From this book, from Bal Mokand Anand, I learned many new things. My way of writing is to present the both sides, positive and negative. From this book, what I really learned is how the family Anand and many students, they saw him a very nice teacher, good father, grandfather, but at the same time, if you read the write-ups, and I deliberately try to find out the write-up from various students, there you will see Professor Anand. On the one hand, he was a very nice teacher, polite, but sometimes it was difficult for some of the students to come along with him. So, the moral of the story is, if somebody asks me to write something, he or she should be careful if I have the document which prove what is being said or it is written, I will not hesitate to use the document. The simple example is Sir C.V. Raman, the discoverer of the Raman effect, the only Indian scientist to win the Nobel Prize until the day. When I started writing, people told me the Raman discovery costed just 300 rupees, then 400 rupees. And I was really not much convinced. Then I tried to find out the documents from the archives, which instrument he had, from where he bought. I had the receipt of these documents, and in the end, I tried to prove this rupees 300, it cannot be correct. The second story, in the Indian Association for the Cultivation of Sciences, there is the so-called small spectroscope with which Sir C.V. Raman discovered the Raman effect. I have proved, I have given the evidences that this cannot be the instrument used by the Raman. Third and the last story. Even there is a film on Sir C.V. Raman. He was still alive at that time. And afterward, he never said what is being written later. The story goes like this. While Sir C.V. Raman was getting his Nobel Prize, he wept. The reason, he said, "Oh, my poor country, India, has not even its own flag. I am getting the prize under the British flag." So I was little bit aware of the story. Then about 6 years ago, a journalist from Delhi, she gave me the call. Due to the science day, she wanted to write something. She asked me, "Do you know this story?" I said, "Yes." She asked me, "Is it true?" I said, "No comment." After that, I started getting the documents. I found the newspaper from that time. I found also letters and also article written by Sir C.V. Raman's wife. She was a brilliant writer. Okay, in the end, the moral of the story, yes, Sir C.V. Raman wept, not due to British flag. He was a sentimental person, and he himself told to a newspaper, he said, "When I got the Nobel Prize, I was very happy." I said, "What an honor is being given to me." And then tears rolled down, and I took my handkerchief to hide my face. So that is how, if the untrained people, they start telling about the history of science, or if a historian, he or she does not recheck the facts, the history looks different. So I'm glad that I have been given the honor to stand here, and I don't think I deserve it. The last instance, whatever I do, it is not only due to me. There are many persons. There are many archives. I always, if you read any book from me, under acknowledgement, you will find the list of all the archives and sometimes the name of the persons. who helped me. You can check this book also. You will find there is at least 1.5 page under acknowledgement. In the end, without you people, without archivists, without a librarian, a historian has no chance to write anything. Thank you very much.
Thank you, sir. I'm sure it's going to be a very interesting read. Today, as we have gathered for the 7th Professor B.M. Anand Memorial Lecture, it is befitting to know about the illustrious life of Professor Anand, a visionary academician and researcher. For this, I invite Professor K.N. Pathak to please come on the dais and shed some light on life and works of Professor Anand.
पानी दे देंगे हमारा बोतल थैंक यू Good morning to everybody. I am delighted to be present on this occasion, and for that I am very thankful to the Department of Physics Administration here, as well as some friends from the Chandigarh Vigyan Parishad who have also asked me to be present here. I really appreciate the department from time to time remembers me and some other colleagues also. That's a very good culture of the physics department. And this tradition, which was established, I think, maybe Professor B.M. Anand's time, but it was very much enhanced when Professor H.S. Hans joined the department. I am associated with the Department of Physics from 13th September 1970. So it is almost 53 years that I have been associated with the Panjab University. First of all, I am very happy to see many friends here. Professor Yusuf, H.M. Yusuf, whom I have heard a lot, but no opportunity to meet, but I know all his senior colleagues. And Professor Yusuf is a renowned scientist. He is a fellow of all the three academies and very good workers. Incidentally, I had a friend Yusuf in IIT Kanpur. I think now he lives in Canada. So he was a very intelligent person and very good friend of mine. We used to meet at ICTP Trieste. So I had also a very close association with VRC, because all the people starting from P.K. Anger, we have been interacting, and there have been several conferences here at Panjab University for solid state physics people. And so people are very helpful to Panjab University whenever we approach them. Professor Harsh Nayyar, he is also renowned botanist, plant scientist, and his work, I am told, is very much quoted in the literature. And I have heard, I never heard anything abnormal about him, because I have been here, although I recognize him by face only today, but I have been hearing his name. Professor Arun Grover has been old student of ours. He was very brilliant student at that time, and Vice Chancellor later he became. So I am very happy that our students, in fact, have been doing very well. I will come to that later. Professor Rajiv Puri, who is the chairperson of the department. Rajinder Singh, I appreciate your efforts to popularize the Indian scientist, which is the basic goal of Chandigarh Vigyan Parishad, which is a sub-chapter of Vigyan Bharati, to promote the science, culture and science temperament about ancient scientists and ancient science which is not known to the general public. So they are bringing out all those things, what was known about science earlier, and that is being promoted by this Vigyan Bharati Chandigarh chapter, and they are also promoting this popularizing the Indian scientists. They are supporting that the old Indian scientists should be brought on the focus and known to the general public. That is the motive of the Chandigarh Vigyan Parishad and Vigyan Bharati both. And I am happy that Chandigarh Vigyan Parishad is doing excellent work. If you look at their activities, they go and organize the school, they go and organize the program in the school and colleges, particularly helping the children in the schools about the science in general, including the ancient science. So they are doing wonderful job. I think it is also supported by the Physics Department, Physics Association, which is old organization, and B.M. Anand's family. So that all the efforts, I think, the concerted efforts is required, and it is very appreciative for the promotion of science and technology and scientists. Coming to the Professor B.M. Anand, when I joined, he was not there. I think he retired 2-3 years earlier before I joined. But I have heard a lot about him. I had a close friend and my student, Professor M.R. Moonga, who used to tell a lot of things about Professor B.M. Anand. I think the B.M. Anand's contribution to science is well known. He got a Ph.D. degree from UK, and his supervisor got the Nobel Prize later. So he was a very good scientist, and I am told that he was very strict teacher, very disciplined teacher, and most of our previous colleagues in this department were appointed by him. You see, I know names, but I don't want to mention. Suman Bala is there. She may remember, I think, similar things as I remember. Well, I forgot some name. Professor Satya Prakash is there. My friend Ashok Malik is here. Professor Khanna is here. I forgot his name because I was so happy to see the faces here that I cannot express. Professor Hans' son is there. Vikram. Kya Dharamveer is there. So I am happy to see many faces. Raja Sandhir is there, who have been there from my time, So for me it is very happy occasion to see the people, because these occasions are rare. Professor Tripathi, and astrophysicist here, I am not able to recall his name, but he used to interact very much with me regarding the space research, and try to write the project, I remember, with a scientist, ISRO scientist, whose name also I did not remember, but he was a very close friend of mine. He himself asked that, you asked the right to project, but I don't know how far it went. There are many friends, so if I don't recall their name, please excuse me. So B.M. Anand, as I was talking about B.M. Anand, so he was a very strict teacher, and he appointed most of the people there. But one thing, again, I heard he was very particular about the teaching. He will not spare any teacher if he is not going to teach his class. There was nobody can afford to miss the lecture and go at time. He used to watch that. People go in time and teach exactly, and then he will get the feedback from the students. So the teachers which he appointed, they are very good teachers in the physics department, you see. And he is also famous. I have known about him that he took brilliant steps along with Professor Joshi, who was the Vice Chancellor then of Panjab University, for appointing very eminent scientists in the department. I think Professor Patharia was one of them. Is that correct? Yes. Professor Khanna, Professor Patharia was of them. He was the first theoretical physicist in this department. And I will speak later about this. And so he appointed Jagdish Mahanti, Sundaresan in particle physics, condensed matter physics, L.S. Kothari, and that nuclear physics who got Padam Shri, P.C. Sood. He was also here. He went to BHU in our time. So P.C. Sood, or maybe 1 year earlier or something like that. So department had a very eminent scientist, but somehow or other, which was also told to me that he was not able to retain those people in the department. So I am speaking from core of my heart, so please don't mind if his family is present here. But he was strict. Somehow all the 4 people, they went soon after joining in few minutes time. L.S. Kothari was also here. So you can see the physics department has been always at the top, starting from the Lahore time. Because Lahore time, physicist who came here, well known is P.K. Kichelu, I think. He was best technical scientist, I think one of the best in the country, maybe in the world, that he brought the culture of technical physics. And many of his students became the director of the CSIO and other laboratories. This is, I think, well known, documented. And Avlak was there, Professor Avlak. Professor Khanna knows more than me. He was a very good teacher, eminent theoretical physicist, mathematical physicist, I will say. So, physics department has always been at the national level as well as international, and many people joined Tata Institute. They used to come, they were associated with the physics department. They used to come and guide the students. So the research culture was introduced by Professor B.M. Anand about the high energy physics, that's emulsion physics, for the discoveries of the particles and things like that. So since then the particle physics has been established in the department, because he introduced already the research culture. So, but later on that was promoted very much by Professor H.S. Hans. I will not tell more about that. But regarding the department has produced top-most students. You know that in any area. Today I only mentioned the physics department. They have an eminent institution. They have gone abroad and made good name in science. They are here, had made good scientists and gone to the various eminent positions. Grover is one of the example here. Ajay Sood has become scientific advisor to the Prime Minister. So you can see these are the brilliant students. So there are many names which can be quoted. So even after we left the university, I left the department to 2001. I retired in 2001, although I continued till 2005 as an administrative position. But I taught up to 2002. 1 year I could taught, but later on I withdrew. That I cannot carry double load of teaching as well as administration, so I withdraw. So I think Professor P.M. Anand's contribution has been significant. Professor Hans took the drastic decision to spread the physics, all areas of physics. I think that was very important. And we are product of that. Myself, Professor Khanna, Professor R.K. Bansal, and then later on we generated people here who were Professor Kia and Jindal and so many other, I think, are the product of this department. So that tradition continues for the physics department. Is continuing, I think. Still, department, I feel, is doing very well. And they are producing good research work. Students are going abroad. That has been the culture of the physics department. That those who do Ph.D., they go abroad. Some of them go abroad and do very good things. And so that is continuing. That tradition is still continuing. So I'm happy about that. Only thing, I hope our Vice Chancellor should have been here, but I will request Professor Harsh Nair to convey that the physics department, I think there is a human resource has been very depleted, I think. So it is time to hire some good physicists to the department that to keep its level continuing at this. You see, many area of science is developing. I am not very much in touch with that, but one thing which I know, I can tell that this semiconductor physics and its application is getting momentum due to the fabrication of chips. You know, fabrication of chips have gone to the 8 millimeter. Minimum 8 millimeter size chips are being used, and the scientists have gone to that level. And the Quad country, 2 of them have signed agreement to come to India to produce the chips. I think $1 billion have been several $1 billion and will contributed by government India, and they are coming to the India. And I am sure, I think, in this decade, by end of the decade, you will see lot of new factories and fabrication of the chips will be taking place in India. So in that direction, I will say that the Panjab University and Department of Physics should take lead role. And I recall that during my time, I took an initiative of starting microelectronics in UIT. I don't think anybody from UIT is present here, but there was a strike in the UIT students in first year itself that they want 2 things. They want that this engineering course would be recognized by AICT, which was not the requirement, because there was act was modified that universities don't need the requirement of the AICT approval. But still, since the campus politics or whatever you call it compressed me to get the approval, I got the approval of that. And second thing, that I had the courses in my courses which I introduced microelectronics, BTech in microelectronics, BTech in software engineering. They were changed because they were not in the list of AICT. And but then we started these 2 courses, I think, MTech instrumentation and MTech microelectronics. And it used to be there in this sophisticated instrumentation center, and they were doing very well. You know, there are only 10 seats of things. They have produced very good students, and they all are doing very well in the industry. All were placed very good position. But somehow or other, this could not be continued. I don't know. I feel very sorry for that. If those students in microelectronics, they could have now become, they could have continued, so the students would have gone to the coming area. There's a lot of job going to be contributed in this industrial production of the chips and things like that. So I think Professor Hasnayer will convey that this should be taken initiative by the university, and also the nomenclature of some of the courses needs to be changed now, because physics department has already got the BSc honors school in electronics, so they can make it very well without any major change to microelectronics. That will be more sellable, and you will get more students. Similarly in UIT, because university needs revenue also. So from revenue point of view, I am saying that the computer science, IT has become an old name. We have BTech in computers, in information technology. It is very old name now, 20, 30 years old. Now the situation has changed in computer science, artificial intelligence, and things like that. So they must be promoted in the university. I took this opportunity to convey to the Vice Chancellor and Professor Hasnayer that initiatives should be taken. There are many areas I don't want to elaborate. Raja Sandhir may know better because he is in the forefront of the administration. So he should also, I convey to him also, that the several new initiatives in the university and departments needs to be taken to keep its standard of the Panjab University, which is international, as you know already. So that will go a long way. And we have not taken any initiative for the last few years. I don't know whether I am speaking correctly or not. My previous vice chancellors are sitting here. So I think we have to take some drastic steps regarding teaching and research. People talk about several things. You know, this campus is very good. I must appreciate our faculty is very good in general. But somehow they divert their attention in many other things. They should, but I think keep proportion to the academics and other things. I don't want to elaborate other things, but this is why I feel sitting outside, and although I don't indulge any, not at all in the Panjab University, but I read the news of the Panjab University because I am so interested, because I spend my whole time, and I must say, Nihswar, I have not taken any special advantage or favor of the Panjab University. That also I wanted to tell here. So I dedicated myself to the Panjab University. Still I am dedicated to Panjab University and Physics Department. I will say again something which Physics Department like or not. After retirement, I came to department after 65 years of age. The department gladly accepted. That's good of them. But I asked that I should be given teaching at that time. But they say that we don't give teaching to the retired people. However, after 1 year, they gave teaching of pre-PhD course to me and Satyaprakash, one paper of pre-PhD course. So both of us taught that course. After that, they never asked that you teach anything. And I think same culture is probably continuing there. I will suggest that Physics Department should take the retiring teachers, continue them, rather than taking the guest faculty or ad hoc faculty. You know, because you don't appoint any ad hoc faculty or guest faculty unless he has done 3 years postdoc for somewhere. That used to be culture before. I think these are the points, smaller points, which people in the university and Physics Department in particular, because I am related to them, so they should take note of this, I think. Professor Rajiv Puri will, I think you're listening. So I think he's a very active scientist. I know, done very good work in nuclear physics. But I think concerted effort of all the faculty members required to continue the tradition of the Physics Department. So I don't know what else I can speak. I have spoken a lot about Physics Department and university. I hope this might send some message. And finally, I again thank my colleagues, Professor Navdeep Goyal, Professor Tripathi, Professor Singh, Professor Behra, Professor Khanna, Professor Satyavkar, and all the people sitting on the dais. I thank you very much for providing me this opportunity. Thank you.
Thank you, sir. As we proceed further, I now invite the chief guest of today's function, Professor Harsh Nayyar, Director Research, Panjab University, to please come here and say a few words.
Okay, good morning, everybody. I'm deeply honored to be in the company of distinguished physicists on the dais and in the audience also. Personally, I know many of them. This department is one of the excellent departments in the university, and we always take great pride of this department. And whenever we talk about listing the departments category-wise in different categories, this department is always listed as number one. And for the upcoming NAC visit also, we have especially put an emphasis that the department the team must go into this department. So this department has produced eminent scientists. They have given us Vice Chancellor to Vice Chancellor on the dais, Professor Pathak and Professor Grover, Satya Prakash is here. Deans and directors, Professor Nadeeb is here. So we are really proud of you. Now we have an honorable speaker today, Professor Yusuf. He is from BARC, who is going to talk about quantum entanglement, which is a very mysterious phenomena, as I understand, as a layperson. And he's going to talk about many intricacies about that. Whatever I understand is that this is about quantum computing and high-tech or faster quantum communications and many other areas which there is a potential. So it's a deep honor for me to be present on this function when you are paying a tribute to a former legendary scientist, Professor Anand, on whose name this auditorium is also named. And I must congratulate Dr. Rajinder Singh for his efforts to compile the information, and he has been writing many books on legendary scientists, which is very important and need of the hour, because most of the younger generation is forgetting about these people. So I must congratulate and appreciate the efforts of Dr. Rajinder Singh. So I would like to convey the entire department congratulations and appreciation for organizing this function in the memory of Dr. Anand. Professor Grover, I think, started this lecture series during his time, and it's highly appreciative. He started in 2015 in our department also in a similar way, where we have a Professor Kashyap Oration Award. So this is great tradition to be continued all the time, where we are inviting speakers like Professor Yusuf and the physics, and we had many distinguished people. This is a great tradition which should be carried out by all the departments. So let's continue the legacy of these legendary people and tell our younger generations what they have contributed. If your department has a great reputation at this stage, it is because of the great roots which Professor Anand had maintained at that time. So thank you for having me here. I'm sure Professor Yusuf is going to tell you more about this interesting subject. Thank you so much.
Thank you, sir. I would now like to invite Professor Arun Grover to please apprise the audience here about today's lecture series, which primarily aims to promote intellectual lectures and foster innovative ideas in physics.
My teachers, Professor Pathak, Professor Khanna, Professor Satya Prakash, my colleagues and my peers, K.R. Dharamveer, Suman Berry, my S12 colleagues from Physics Department, Navdeep, Professor Mehta, Professor Pathi, and many other younger people. Professor Bari, especially invited today's event, is our former registrar and also an emeritus professor in the chemistry department. Several heads of the university departments are also present there. Several colleagues, teaching colleagues from the university are also present here. Here, Professor's name has been mentioned by several of them already, and I'm very happy that Professor Harsh Nair came representing the university at today's event. To my young friends, let me confess that I was once a student like you in this department, and today in particular is a day of fulfillment for me as a student of this department, as a faculty of this department, and a later part of my career as a VC of this university. 11 years ago, precisely on July 21, 2012, when I left Bombay to accept a position at the university, I came with just one lofty idea. I had become aware of Ruchiram Sahni during the commemoration of Homi Bhabha's birth centenary year. I knew about the connections between Bhabha and Bhatnagar while being a member of the TIFR staff and also someone who was given the charge of commemorating Bhabha's birth centenary. But other than that, I didn't know much about the university. So I said, when I go to the university, we will commemorate 150th birth year of Ruchiram Sahni in the backdrop of 150 years of higher education in Punjab, on the premise that Ruchiram Sahni was born in 1863 and the Government College Lahore started in January of 1964. So 2013 will be a year, 150 years would have passed since the initiation and evolution of higher education per se in Punjab. So my information base was sort of limited to this thing. But over last 11 years, I have gone through an uncharted path. I learnt a lot. Every day I am learning something about my own heritage, which I did not know while I was a student here or while I was a teacher here. And I said it's a day of fulfillment for me, because large part of what I gathered about my own heritage, and I believe my life would have been incomplete if I had not explored that heritage, I have tried to record in the prologue of this book. If you read the prologue of this book, okay, it has subtitles like, and I have said, I have tried to record my comprehension of beginnings of teaching and research in Punjab per se, but actually the entire India as per se, because whatever regulation of education in India started only after the annexation of Punjab. So the first 3 universities of India came up only after the annexation of Punjab. So if you seek comprehension of education and research in Punjab, you actually seek a comprehension of education and research in India. And this has become very important today, while we are saying we are going to implement a new education policy which will do something great for the country. It would indeed do great for the country, just as the honor school education introduced at University of Punjab at Lahore in 1919 did a great job for nurturing science and research in northwest, whole of northwest of India. And I have often given talks at various forums in the university and as well as elsewhere in the country on the rich scientific heritage of northwest of India. So every department of Punjab University has a very rich heritage. Physics department, honor school was of course the last to start in Lahore, 1934. The honor schools in rest of the subjects had been started in 1990. Right? So first honor school to flourish were the botany, chemistry, zoology. Maths didn't have an honor school. Maths honor school came in much later. But the school of maths, or the school of number theory at Lahore, was next only the school of number theory, which started at Madras, and Ramanujam came out of that school. Anand Rao was the starter of that school, and the number theory school at Lahore was in some sense commenced by Gopal Singh Chawla, whose son Sarvdaman Chawla was one of the greatest mathematicians that India has produced in the 20th century. After Ramanujam, Harishchandra, it is Sarvdaman Chawla. So this maths building is named after Hansraj Gupta. Hansraj Gupta Hall. Hansraj Gupta studied mathematics both under Gopal Singh Chawla as well as his son Sarvdaman Chawla. Okay, so that is why that building is named after that. The Kashyap Hall is named after Shivram Kashyap. Shivram Kashyap is the first researcher at Lahore. He was a medical doctor who drifted into teaching biology and then became the greatest botanist. And Birbal Sahni was a student, M.S. Vallabha was a student, A.C. Joshi was a student, P.N. Mehra were his students, etc., etc. Chemistry building is named after Gurudat Vidyarthi. Who was Gurudat Vidyarthi? Gurudat Vidyarthi was a contemporary of Ruchi Ram Sahni. Who was Ruchi Ram Sahni? Ruchi Ram Sahni was the first teacher of physics and chemistry of Indian origin who joined Government College Lahore in 1887. Gurudat Vidyarthi, Ruchi Ram Sahni, and Hansraj, who started all these DAV schools and DAV movements, they all passed intermediate examination of Punjab University in the year 1882. So every department, every building of Punjab University, every hostel of Punjab University which is named after someone has a story to unfold. So one of the purposes of my encouraging eminent historian based in Germany from Punjab, who has been writing about C.V. Raman and all the Calcutta scientists, to start writing about Punjab is to one day have a compilation of stories of every building of Punjab University. Some years ago, Rajinder Singh wrote this book I have with me. It's called Dazzling Dawn, the physics department of Calcutta University. He also gave a talk in our physics department during his last week. He spoke about it. So, every department of Panjab University can have a book like this. Okay, it will be as inspiring as this book and will tell the heritage to the young people about the rich heritage we have had. And it is worth telling because it is indeed very, very inspiring. I am going to give a talk just 1 week from now at TIFR telling about the scientific heritage of northwest of India. But actually I am going to tell the stories of contemporaries of Shivram Kashyap, Homi Bhabha, Hargobind Khurana. Okay, these are the 3 or 4 people. But now, Ruchiram Sani is a contemporary of, for us, contemporary of J.C. Bose and P.C. Ray. Shivram Kashyap, for us, is a contemporary of people who are born in 1880s. And that is, in that are the people like Ramanujam, C.V. Raman. So Shivram Kashyap, Sahib Singh Sokhi, they are a very eminent chemist, Baba Kartar Singh. They are all contemporaries of Shivram Kashyap. Then there are contemporaries of Bhatnagar, and there is a whole list of names that I can tell you. Then there are contemporaries of Baba, they are contemporaries of Khurana. Bamba is a contemporary of Khurana. Yashpal is a contemporary of Khurana. So there are all these contemporaries of famous Indian names that you may be aware of, and Punjab has a very significant contribution in the scientific heritage of India. 11 out of 40 presidents of INSA have a Punjab origin. I learnt it only recently. There is a book by Professor Kohli on 200 sparkling Punjabi scientists. While scanning through that book, I came across this statistics that 11 out of 40 presidents of INSA are from Punjab University. So, it is just a chance that after becoming the VC, via Dr. V.C. Sani, who was a senior colleague at BRC, that I became aware of Dr. Yogi Anand, son of Dr. B.M. Anand. Vinod Sani's sister is married to Yogi Anand. The Anand family wanted to do something for alma mater of B.M. Anand, and that is how the story got unfolded of initiating B.M. Anand lectures. So today is the 7th B.M. Anand lecture. Anand family wanted Professor Yashpal to give the first lecture. Initially when they said this, I wasn't aware why they are so keen to have Yashpal give the first lecture. But indeed, Yashpal was a student at Lahore. He had done his BSc, and he was in the final year of BSc honors school when the partition happened, and his education had to be completed in the physics department, which went from Lahore to Delhi. It went from Lahore to Delhi because Kichlu, who was the first student of Meghnad Saha, who had joined Government College Lahore in 1929. I mean, he left Lahore 8 months before Indian independence. January of 47, he left Lahore. He went to Delhi, where Kothari was there. Kothari was the second student of Meghnad Saha. Actually, Meghnad Saha had sent Kothari to work with Rutherford, and he came back, and he was then a professor in Delhi from 1930s onwards. So, all these connections I have found it only in recent. For me, these are very inspiring. How Kichlu, a first student of Saha, he was a theorist, and Professor Pathak told us that he was an experimentalist. Yes, Kichlu was a great experimentalist. He even set up company. He went on to be the director of NPL, and so on and so forth. So there is this great tradition of Indians, theorists who became great experimentalists and inspired great experimental science. And B.M. Anand is an excellent example of theorists inspiring fresh MScs to take up independent research and excel in them. If you read this biography, okay, I wasn't aware of it till Rajinder Singh sourced out all these things, and then it figured out. B.M. Anand worked in 6 fields at Lahore. He didn't have a Ph.D. at Lahore. It was not required. Only when he comes to Hoshiarpur, and now he is a part of the university, and the physics department is created for the first time. for the university, only at Lahore, only in Hoshiarpur. The physics department at Lahore was an intercollegiate faculty. If you go to page 11 of this book, you will find Board of Control for Honor School in Physics, Faculty of Physics. And you look at the Faculty of Physics at Lahore. It is an intercollegiate faculty. It is people drawn from different colleges. J.B. Seth, who was a government college teacher, and he is the one who started to do real research at Lahore from 1924 onwards. Okay, he is the head of the department. He doesn't have a PhD. So there was no motivation to do PhD at Lahore, to continue to do research or be a teacher at Lahore. Only when B.M. Anand comes to India, and now there is this, universities are regulated by independent India in a different way, and he cannot become a professor at Hoshiarpur unless he has a PhD. So at the age of 50, he goes on a Government of India fellowship to England. So he's head of the department. He's one of a PhD fellowship he takes, Government of India fellowship, which is given to fresh graduates to go and do PhD. B.M. Anand takes that and goes and works with Powell. Powell was already a Nobel laureate by that time Anand went there. He goes there, he's an experienced researcher. He has so much of research to his credit. Working in a different area and just writing a PhD thesis is a child's play for B.M. Anand. And this is what he did. In 2 years' time, he wrote his thesis, he came back, he's a professor and now head of the physics department at Hoshiarpur, and he starts progressing the department. And then departments becomes a multi-dimensional department. His earlier training is in electric discharges, what the research used to work. Then the work that he did with Kichlu, and then he made the Raman spectrometer. 1 year after Raman gets a Nobel Prize, B.M. Anand had made the Raman spectrometer, and he wrote 2 papers in reviews of scientific instruments on the Raman spectrometer. All this I learned courtesy research by Rajinder Singh. So for me, whatever I didn't know Rajinder Singh until 2019. Actually, I only corresponded with him remotely because he wrote this book. Okay, he wrote this book on Bibha Chaudhary. Okay, so Bibha Chaudhary is the one who had discovered pion in Calcutta, which Powell did a better job with improved and better resolution, better quantitative analysis, and that is how Powell got the Nobel Prize in 1950. So when Rajinder wrote a book on Bibha Chaudhary, star unearthed, then the Indians get up. Oh, there was an Indian woman scientist, first woman scientist to be employed by Homi Bhabha at TIFR in 1949 when she returns from England after having worked with at Manchester with Blackett. Blackett also got the Nobel Prize. Blackett got the Nobel Prize earlier than Powell, so that is how Bibha Chaudhary went and worked with Blackett. Long stories, but I came to know Rajinder Singh only after he wrote this book on Bibha Chaudhary. Because he wrote a book on Bibha Chaudhary, he went and he also wrote a book on a first woman PhD from Calcutta. Okay, that he got motivated to write a biography of Suman Beri. Okay, and you are all aware of biography of Suman Beri that Rajinder wrote, and this book was inaugurated online. Rajinder was in Germany when we inaugurated this book during the pandemic online. So B.M. Anand's book is the second book written by Rajinder on Punjabi scientists, and this is the first book that is being released online of Rajinder in Chandigarh. I had gone with him 6 months ago to release 2 books in Calcutta, accompanying him. So by now people know Rajinder Singh. He has already written 42 books. He is a celebrity in his own way. He is a school teacher who is attached to University of Oldenburg's History of Science unit, and it is that involvement which gets us so many books. I hope our university also creates a history of science unit, because there is so much to be written and recorded about Punjab University's history. It's not Punjab University's scientific heritage, it's the scientific heritage of whole of northwest of India. So our university should take the initiative to create this unit, and we don't have to look to UGC for this. There is a foundation for higher education that Punjab University has, and that has enough financial strength that in a small way we can initiate this project on history of science. We should get the heritage of scientific heritage or the academic heritage of Panjab University. It is not just the scientific heritage, the heritage of academic heritage of Panjab University should be taken up as a project by Panjab University. Rajinder is going to retire as a school teacher in Germany. We should engage him, invite him to be a visiting professor, take his help, okay, and have this project going. And once in a year, we must assemble in one or the other department for a function like this. You know, so many departments in the university today have this oration lecture. There is a Shivram Kashyap Memorial. There is a Sarvadavan Chawla Memorial Lecture. There is a G.P. Sharma Memorial Lecture. There is a P.N. Mehra Memorial Lecture. There is a O.P. Vij Memorial Lecture. There is Baba Kartar Singh Memorial Lecture. There is R.C. Paul Memorial Lecture. So, Bhatnagar Memorial Lecture. There are so many memorial lectures in the university. And I think for next 10 years, every year at the start of the year, we can have a function like we are having today. Okay, where we should celebrate our, I should say, recent past, not distant past, because students of these people, BM students are there in Punjab, Haryana, you know, students of R.C. Paul are there everywhere, students of Mehra are there everywhere, students of S.R.K. Chopra are there everywhere, you know, students of Professor Baba are there everywhere from biophysics. You name it, every legend of Punjab University has students who are permeating the universities and colleges in not only northwest of India, I would say rest of the world also, because the students who graduate from the honor school, you know, they permeate the whole world. And it is only from Rajinder Singh's book that I came across these few lines, and with this I will conclude. Okay, what is the purpose of honor school? Okay, in the 1945, the yearbook of Panjab University at Lahore. What does it say? It says, teaching methods about the honor school. Okay, it says, teaching, it was stated that the teaching in the honor school shall consist, so far as may be possible, of discussion between teacher and student, guidance in reading and criticism of written and practical work, with attention to the particular development of individual student. Guru Shishya Parampara was what was to be followed in the honor school. So far as may be possible, it shall exclude, it says, it shall exclude the use of textbooks and the delivery of lectures intended to be recorded and memorized like textbooks. So the honor school students are not supposed to memorize things and vomit it out in the exam as a mugged up material. It is supposed to be innovative teaching. So this, what the NEP is wanting to promote as a 4 years of graduation, as an innovative way of taking people to a higher level of thinking process. This is what Panjab University had started to do in 1990. And it is not an original idea of Panjab University. The idea of having an honor school type of an education where you spend 1 extra year getting a graduation degree actually came from Madras in 1912. So this difference between the pass course and the honors course, we called it honor school, where you spend 1 extra year, okay, where you teach physics, chemistry, maths for 2 years as if it's like a pass course, but then you specialize in a given subject and reach to the frontiers of that subject. And then you engage for 1 year research and you get your master's degree. So new NEP is back to the same thing, which is more than 100 years old. And it is this NEP via which we are hoping that at 2047 India at 100 would be different from India at 75 in 2022. So I don't know whether I have made sense, but this is a kind of message I wanted to share with all of you, that the honor school students of this university are privileged because they have at least 100 years experience behind it when Panjab University will implement the NEP, the new NEP. So when the NAC visit happens, I think it should be told to this NAC peer team that for us it is nothing new. We may be short of resources today because the government is a little stingy in giving us the resources. If the government loosens its purse strings a little bit, if there is one conventional university of India which can demonstrate the implementation of NEP in a state university, it is this university, and they better give few crore rupees extra to Panjab University every year so that it can emerge as a model university to implement the NEP, current NEP. Thank you very much.
Thank you, sir. Before we make way for today's lecture, we have a small video sent by family members of Professor B.M. Anand expressing their thoughts and gratitude. So we will play that first.
Good morning. My name is Samir Arya. I'm one of the 11 grandchildren of Professor B.M. Anand. I'm speaking to you from Austin, Texas, USA. I'm also the son of Dr. Shada Arya, who is a Ph.D. graduate in physics from Panjab University. I'm here to represent the Anand family. I really wish I could be in Chandigarh in person today. I have a family obligation that keeps me from attending. I'd like to start by thanking the many of you who made this event possible. The Anand family would like to extend our warmest thank you to Vice Chancellor Dr. Renew Bij, the esteemed guest for the presence at the launch of the biography of Professor B.M. Anand, and to Dr. S.M. Yusuf for gracing the occasion in delivering the Professor B.M. Anand Memorial Lecture. We are indebted to Professor Arun Grover for initiating this project, for his enthusiasm, encouragement, and pursuing this project to its completion. We are grateful to Dr. Rajinder Singh for undertaking this project. Dr. Singh has done brilliant work to illuminate and highlight the work of many Indian scientists. Dr. Singh diligently collected the material about Boji's journey from a young student to an inspiring teacher and dedicated research scientist. We are honored that he has included Boji in his collection of work. My family and I have worked with Dr. Singh for the past 2 years on this project, and I'm so happy the universe has brought us a new friend in Dr. Rajinder Singh. Dr. Singh, I'm very sorry for not being there to meet with you and celebrate with you in person today. We express our sincere thank you to Professor Nadeep Goel, Professor Devinder Mehta, the faculty, students, and participants of the Physics Association for their help. Our thanks go to Dr. Arvind Garg and the Chandigarh Vigyan Parishad for publishing this biography. Professor Anand's family and friends called him Boji. This is a Punjabi term to show respect and affection, and how I will be addressing my grandfather today. I'd like to talk a little bit about what Boji meant to our family. He was always a teacher at heart. He took every moment to explain and teach with patience. He had a magical way of gaining your attention if you were the youngest child to the most respected adult. The way he interacted with you, you wanted him to teach you. I was very lucky to be able to spend a great deal of time with him when I was young. As a child, of course, we learned about math and science. But he put the same dedication to teaching us so much more. Everything from gardening to playing card games to the physics of cooking. The biography details many stories that always come back to the passion for teaching. Boji didn't limit his passion to just teaching. I think he equally had a passion for learning. Boji showed us that we can always keep learning. The book will chronicle stories from our family about how he wanted to learn to use a PC for the first time so he could write his memoirs. He also loved to learn about computer games from his grandchildren. He didn't get to see the rise of the internet, but I could only imagine how engaged he would have been with access to the web and the fun he would have had with tools like ChatGPT. I hope you can find many stories of the biography enjoyable as we did in collecting them from our family and friends. I hope the Punjab University students can find inspiration from this biography as well. It may be a cliche, but Boji showed that anything is possible. You will see that Boji grew up from the most humble of means in pre-partition India. And through education, hard work, and perseverance, he made some fantastic accomplishments. As you can see, his legacy is all around you today. I think this is a great lesson for any student. Once again, my family and I would like to thank the guests, faculty, and students at Punjab University for holding this celebration, and I hope you enjoyed today's lecture. Thank you very much.
This book is virtually the family. Every student of this department will get this book free.
So we now move towards today's lecture. We are honored to have Professor S.M. Yusuf, Director Physics Group, Bhabha Atomic Research Center, who will be delivering today's talk. For the introduction of the speaker, I now invite Professor Navdeep Goyal, Dean Faculty of Sciences, to please come.
I have the honor of introducing today's speaker. As has been already told, currently Professor S.M. Yusuf serves as Director Physics Group and Head Solid State Physics Division, Bhabha Atomic Research Center, Mumbai, and Senior Professor at Homi Bhabha National Institute. He is an elected fellow of all three major Indian science academies, that is, Indian National Science Academy, Indian Academy of Sciences, and National Academy of Sciences, India. He is an internationally recognized expert in magnetism and neutron scattering, having diverse contributions in the fundamental understanding of magnetic ordering and magnetic phenomenon. He has an impressive record of research outcome with nearly 300 research articles in international peer-reviewed journals, and his Google Scholar H index is 51 with approximately 9,000 citations. Dr. Yusuf has established himself as an international expert in the domain of magnetism and neutron scattering. He has also made noteworthy contribution in one-dimensional and two-dimensional spin systems by revealing new magnetic phases driven by competing interactions, quantum fluctuations, etc. Very recently, he has succeeded in experimentally detecting the presence of strong quantum spin entanglement up to near room temperature in a copper-based trimer spin half-chain quantum material by innovative neutron scattering study. And obviously, such development of new quantum magnets is highly significant in upcoming quantum technology. Significantly, Dr. Yusuf has built a prototype artificial heart pump support device based on magnetic nanoparticle loaded medical grade membrane and obtained international patents also. He has delivered more than 200 invited and plenary talks in various national and international forums and is serving on many academic committees of different institutions. I'm sure that his talk will be quite useful, particularly for those students who want to start their career, particularly their research career in physics, and because the kind of work that he is doing is certainly going to be quite useful for many students. Thank you very much.
And how to go to next? You can go to from here, or अगर इसको और zoom in करें. I'll go full mode. Full mode. Then next. Okay. By sliding. No. Why is it faster? It goes up or down? No. Go to first. That is true. Then next is going sliding which way? That is it. No, that's the problem. No, there is no problem. You can click from here. Okay, so go up. Go down. From here you can go back. Go back. front, you can move this.
Thank you, Professor Navdeep Goyal, for your kind introduction. And before I deliver this 7th B.M. Anand Memorial Lecture, I must thank this organization, the Panjab University, particularly the Physics Department of Panjab University, for this kind invitation. I am really happy to be here. And in my talk, I will be showing that how much interaction we have, particularly with the Department of Physics of this university and the physics group of Bhabha Atomic Research Center, where I come from. And I also like to thank Professor Puri for the kind invitation, of course the Vice Chancellor of this organization, and Professor Pathak, Professor Grover, and all other distinguished delegates and who are behind this program. Actually, as you all learned, that Professor Grover who started this lecture series, and that's why today here, and the great job that has been done by Dr. Rajinder Singh, that today we have released this book, and that is the inspiration for all of us, and that is what has brought us together for this presentation. But when you want to talk about, I am starting at 12, so I have to be a bit faster. So when we talk about the physics or science in the country, we must see a little bit literature, what we are talking about, what is the time scale, where, if you see the Panjab University, as you all know, and it has been said in many ways, so it was established in the year of 1882, in Indian history, the first university, or college rather, it was in 1818 at the Srirampur in West Bengal. And after that, of course, IIT Roorkee comes, University of Calcutta comes, and as you all know, this when in 1882, it was at Lahore, and then of course relocated in Chandigarh in the year 1947. Now, Professor Anand, as you all heard, that he took over as head in August 1949, but of course he was appointed. The physics department of this Panjab University started in the year of 1934, which I learned, and that time only Professor Anand was appointed as a lecturer and then became head of the department in 1949. And of course he continued until 1967, and particularly this physics department is physics, there are very strong activities over the decades on particle physics, nuclear physics, solid-state physics, as you all know, and we are very happy that this kind of strong science program started quite early in this part of the country, and that has taken us today here. Now, when I talk about the Panjab University or Physics Department of Panjab University, we must also see at that point of time, how was the Indian scenario with respect to physics, and there we must talk about the University of Calcutta Department of Physics, and also I am from that part of the country where my education was there, and you see this Calcutta University Physics Department started in 1916, some years before compared to this, and that time who were the lecturers, first D.M. Bose, C.V. Raman, and of course later on Meghna Saha, S.N. Bose, Shishir Kumar Mitra, and V.C. was Sir Asutosh Mukherjee. So this is the era we are talking about, and we need to appreciate that what today we are benefiting, sitting in various physics activities, because of all these visionaries, physicists who contributed immensely for the growth, for the nucleus of physics activity in the country, and today we are here, we are enjoying that. So this is a great moment for us, and Professor B.M. Anand is definitely one of those to be mentioned in this. Sorry. Now this is the problem. Some problem happens. I have to go back, right? No, where is that? Just have to go back. Okay, so probably I'll Is that okay or small enough? This will be more, it's okay. Okay, and when we talk about Professor B.M. Anand, we must see, what kind of reputation he had from this, from this recommendation letter for his professorship in the Department of Physics, and very, very strong record. So that is what we all learned from the earlier speakers. Now coming back to this introduction between Department of Physics of Panjab University and BSc DAE, and I will be restricting only with respect to physics because we are talking about physics here. And you see, as late as March 1961, this DAE 7th session of Cosmic Ray Symposium was held in this department, which is to be noted. February 1964, all are before I was born, all these activities. 64, 8th Nuclear Physics and Solid Physics Symposium was organized by DA in this department. And now, of course, as you know, these two symposia are held separately because it has grown massive. And 1966, there is a project which is called Application of Mass Spectrometry in the Field of Nuclear Geology that was sanctioned by DAE. And there are many such examples. I cannot be listing all. There is a strong introduction in recent time during 2005 to 2022, collaboration between the Nuclear Physics Division of Physics Group of BRC and the Department of Physics. Many of you are involved in that, whether it is CMS collaboration, whether it is utilization or doing science using BRC, TFF, electron LINAC facility, or joint BRNS project. So this kind of strong interaction is already there, and it is it started much earlier, right from the beginning. And I am very happy to be here with you, and thank you so much for the kind invitation. It is my pleasure to be here. Now coming to the talk, the title of the talk which I have given, the revealing spin quantum entanglement by neutrons. See, neutron is a fundamental particle, and we get from the nuclear reactor, which comes from nuclear fission, and that is the unique of DAE, Department of Atomic Energy. And we have a research reactor where I myself have built neutron instruments, and we have been using for knowing the materials property, particularly we are talking about the spin properties. But before I go to the details, I would like to touch upon this aspect because there are many research scholar students I see that what to understand by entanglement, and that even spin entanglement and quantum. It is definitely a quantum property. So I like to go little details of that. Now before we go to quantum, historically if you see how the physics has evolved, how science has evolved, so the classical concept you all know, the two distinct categories. One is the materials body, that is any particle, apple falling from the tree, Newton's laws of motion, it can describe the position and velocity, momentum very precisely without any difficulty. You have on the other side, you have the one side is particle, another side is wave, that is electromagnetic wave, which are described by 4 Maxwell equations. And of course you also have the law of thermodynamics. These 3 are the building base of the classical physics, classical mechanics, as you all know. And there is no need to think any other way. You can describe 100% fully. But the difficulty comes. Now I have to go to down. So this way. Yeah, now I manage. Yes, but the difficulty comes from this kind of observations, and these observations are nothing but that led to the birth of quantum mechanics. So the one is the Planck, that wave may also behave like particle. That is the Planck hypothesis, the photon quanta. So light is known as wave, but it behaves like a particle, that is the photon. So that, and another way, the particle is particle as per classical mechanics, but particle can behave like a wave as per the de Broglie hypothesis. And then position and momentum of a particle cannot be measured accurately simultaneously, which was possible as per the Newton's laws of motion. So this is again another difficulty. So that's why the Heisenberg uncertainty principle has to come in. Then energy of the wave is quantized, equal to NH nu. So all these four have to be brought in order to explain the observed effects, observed physical phenomena. And that's why the requirement of something more than classical mechanics came in, and that was the quantum mechanics. And these four physics phenomena, physics observation, essentially the birth of quantum mechanics. And this is distinctly different from the classical mechanics. Now, if we want to visualize a little bit more, the classical versus quantum, see why I am talking all those things? Eventually, I will be talking about quantum entanglement, quantum spin entanglement. So we must know what is quantum mechanics, where the classical mechanics fails, and then eventually we will be talking about the spin quantum entanglement. We will be talking about the utility of that. Why are we bothering so much? Is it only of fundamental interest? No, it has great implications for the quantum technology, quantum computer. This is what will be my journey in my talk. When we talk about the classical, let us say I have a gun, I am just firing bullets, throwing marbles, throwing balls, and we have two slits. That's the Young's double slit experiment I am referring to. We have two slits, and when I have this kind of macro objects, I have no difficulty. If one particle, one bullet goes through the slit 1, you can know a thing that it has gone through slit 2. It has gone only through slit 1. And vice versa. If the nth bullet has passed through the slit 2, it has 100% passed through slit 2, and there is no question of bringing the roll of slit 1. This is the meaning of that. That means particles are 100% distinguishable. That is the classical mechanics, as you know. And for this, the profile is like this, and for this, which passes through this, profile is this. And what you see on the screen, total profile, is somewhat enveloped like this, or it is the addition of these two. So this is a simple algebraic addition of these two profiles. This is what our classical concept, when you deal with the bigger object, macro object. Okay, what I mean by macro, it is millimeter, nanometer, this kind of objects I am talking. But if you take some elementary particles like electron, and you have a gun, you have electron beam, you are sending electrons, then the experimental observation, to 1 and 2 does not hold good. And the pattern changes, it gives maximum and minimum. And this can addition of these two events, what you see on the screen, but rather phi 1 plus phi 2 mod square. That is the beauty of that. That means the mod square phi 1 phi 2 mod square, and you see what is the physical interpretation of that. That means if you are thinking that my electron, let us say electron number 1, it has passed through slit 1, it has no relevance to slit 2, that does not hold good. You do not know it has passed through both. It is that kind of scenario, So that means the electrons are not distinguishable. That is the difference between these. That's why you have this interference, and so-called it is called quantum interference. Okay? You can take another example like this. You have two oscillators and they are coupled. You can, you know, in a material you have atoms, they vibrate. You know the atomic chain in the solid state physics book you have read, and atoms are vibrating and they are coupled with the spring constant, so which you now know as phonons, the coupled atomic vibration. But you see two oscillators when they are coupled, if you have a classical solution, you have the Hamiltonian, kinetic energy of 1 and kinetic energy of 2 and the potential, and then solution comes just a product of solution 1 and product of solution these two, okay, oscillator 2. But in quantum mechanics, it is not this way, it is this way, okay. This is the state in quantum mechanics. So again the interference, you know. So you can have examples like two ions in a laser trap and they are oscillating in a coupled manner. So basically, basic postulate then in quantum mechanics, you deal with the wave function. Formed by all these quantum particles. So here we have two states. So the combined wave function, where you can have both spin up, because spin up you can have projection both up or both down. You can also have these two combinations. So this is what you have learned in quantum mechanics. Okay, that the spins or states can have all these four possibilities. When you have two spins, you want to have a composite state. And these two states, both the plus minus, of course this is antisymmetric, these are entangled state, okay? These are entangled states. So please note that this entanglement word in the history of quantum mechanics, it has come very recently. See, if you go back to your old, the quantum mechanics book, you will see this word is missing because it is a new concept. But essentially, this is what is the wave function we are talking about, this antisymmetric or symmetric wave function we are talking about. So general state of two entangled spin is this, A and B plus minus. So this is the central message of this when you talk about entanglement with respect to spin. And this is the entangled state. These two are not entangled, okay? Now, why do you bother about the entanglement? Because, as I said, it has relevance. Because when you have two states, let us say up is this one and spin down another one is this one. So these are called, two spin states, they are called bight. But when you have a combined state, which is this one, that is called the qubit. And this is the qubit, which is the fundamental unit of quantum computing. That's why we need to bother about the composite state, entangled state, because this entangled state is only the qubit. This is another name. So that's why the spin entanglement, quantum entanglement is so important, because this is the building block. This is the building block of quantum computing, quantum technology. So this must go, but just getting qubit is not enough. if you have to go for quantum computing. We have to go much more. What are those? We have to have easy access and control of these quantum qubits. How to control them? With better coherence, scalability, measurement access, and so on. I'll be touching upon this aspect at the later part of my talk. So that's why this qubit is the fundamental. I'm trying to repeat this. Yeah. Now, is it, as I said, qubit spins are not having monopoly in terms of the qubits. You can make qubits not only with spins, as I just said, you can also have with the energy levels of atom. You can also have qubits with respect to photons. You can also have qubits with respect to trap ions. There are many ways to make qubits. In other words, if you want to build a quantum computer, you can use any one of these quantum approaches to make the quantum computer. Not necessarily you have to rely only on spins. But I will be touching upon spin because I work in the field of magnetism. I deal with the electronic spins, magnetic materials. So that is what is mine. And as you know, in last year, Nobel Prize was given in quantum entanglement, and that was in the area of quantum optics and atomic physics. And these three professors, they shared the Nobel Prize, one-third, one-third, one-third. Now, when you have to have quantum entanglement with respect to spins, electronic spins, see, so far I said you have two spins. If you have this kind of high state, combined state, it is the entangled state. But when you read quantum mechanics, you know, this is like imaginary. Where is my electron? Where is my electron? And how do I get those states? How do they form the, psi? Means it is like imaginary. You have to think somewhere it is there. But in real life, it doesn't go that way. You have to have a material. You have to have atomic spins nearby. Okay? And they have to have that, form that kind of state. So that is the job of the, experimental physicist like me, what we do in real life, to look for materials, look for quantum materials, look for quantum magnetic materials, where I can have the realization of this quantum entanglement out of these electronic spins. But there are certain criteria. You will not even get, these are the latest criteria, you get literature in full-fledged, how to have the quantum entangled spin state in a real system, real material, what are the ingredients you should be putting in so that it might give you. So these three ingredients, and this is, I have been working, I started working in this area quite early in the year of 2006. Since then we are working, and from my research experience, I am writing down these three novel criteria. You should be making a magnetic material out of lowest spin, that is spin half. How do you do? As you know, if you make a compound with copper 2+, and if you know as per the Ohm's rule, you would be dealing with copper spin half. But if you have manganese 3+, you know spin will be larger. So your chance of getting the quantum entanglement will be much lower. So go for the smallest spin value, that is spin equal to half, means only 1 ampere electron, as you know. Then low dimensional system. System means magnetic material where the dimensionality is not 3D, either it is 1D like a chain, spin chain, or it is planar 2D. So, but it is not 3D. So that kind of magnetic material you grow, you prepare in the lab. And third is that you have the arrangements of the magnetic atoms in the samples, means in the material, in the compound, such a way that it causes geometrical frustration, and that is nothing but one individual electronic spin, if it experiences, let us say from this neighbor, it experiences positive X interaction, which is quantum mechanical, from the other one it experiences negative X interaction, so this is under frustration because there is a competing X interaction. This spin does not know which way to align, up or down, and it causes the magnetic frustration, spin frustration, in terms of its orientation state. So that is called the phase. So these are the ingredients you put in, you make, you grow a material, you try to look for a compound where these are more or less there, then your chance of getting the entangled spin state, which I have written here, is much, much higher. That is what. But not necessarily you will get it. There are other issues. And as I said, I have been working my group in this kind of material, and these are the schematic presentation of this kind of material. First, all these are 1D, either uniform chain or spin diamer, uniform timer, or 2D lattice, like a square lattice. Spins are arranged in a square, honeycomb, kagome, triangular. I have worked on all these kind of systems, in real material I am talking about. But you may again wonder, I am talking about the real material, but when I talk about the spins, it is looking like a chain or a plane. So I have not grown any thin film or just tungsten layer. I am talking about real material, crystalline compound, as far as the atomic periodicity is concerned. So as far as the crystal structure is concerned, it is a 3D material. But 3D material, when I look for magnetic atoms, because non-magnetic atoms, they have no prism. Okay? So only magnetic atoms they look for, either they have formed only chain, and chains are not interactive, or they have formed a plane of this kind of geometry, and between planes they are not interacting because maybe separation is such that their quantum mechanics interaction cannot propagate. So in this kind of scenario, you get this. Out of real 3D material, magnetically you get low dimension, 1D or 2D. So, yeah. Now, as I said, Newton is a fundamental particle, and Newton comes from reactor, Dhuba research reactor, where we have the facilities. Newton is a tiny magnet. It carries minus 1.913 nuclear magneton because it has a spin half. So this moment of neutron will interact. I have a magnetic material where I have electronic spin, electronic moment in a material. I am bombarding with Newton beam. So Newton has tiny moment, magnetic moment. This magnetic moment of neutron and my magnetic moment interact, dipole, and that gives you magnetic scattering. That means it is like X-ray diffraction, but more than that, because if you have magnetic atoms, magnetic atom electricity, magnetic moment in a sample, that is dictated by Newton over and above the positional periodicity of atoms. So this is the advantage, and this is the picture inside the reactor hall of Dhuba Research Reactor, nuclear reactor, which is there in Bhabha Atom Research Center, and we have built all these instruments. I have personally built this one, and my other colleagues, so we have been using that. Of course, we do certain experiments abroad as well, which are not feasible here for various reasons. So as I said, another 3-4 slides, I'll just, without talking about the mass physics, I'll only say in a real 3D material how to get low dimensional magnetic material. For example, here is a structure. This is the compound. This is the oxide compound as you see. But when you look at the crystal structure, you see atoms are like a chain. But along this chain, you have magnetic atoms. Now, 3 chains, they form this kind of lattice. So this is the triangular lattice, because in a plane, they form a triangular lattice of magnetic atoms. So as far as magnetic atoms are concerned, they are along the chain. So it is like a quasi one-dimensional magnetic material, though crystallographically it is a 3D material. Okay? Or we have also studied this kind of chain, where the atoms are as a chain, one chain, second chain, but the chain separation is such that, and also there are non-magnetic atoms like this J3, which is the X-ray interaction between this chain spin and this chain spin is very, very weak, negligible. So you will end up almost like a 1D chain. So this is the sense I am trying to bring in a real world, how to get the low D materials. And we have been And you can have this kind of crystal material, where again magnetic layers are there, and their manganese is the magnetic and it is forming a square lattice. So I was telling how to get this kind of low D magnetic material out of 3D world, real life samples. And then we have also worked on this kind of material. Again you see here you see copper layer. Copper forms a square lattice. But between two copper we have non-magnetic strontium, Professor Tripathi is here, niobium, O6, these are all non-magnetic, and this separation is about 11 angstrom. That means these magnetic layers, they cannot interact magnetically. X interaction is 0. So that means effectively is concerned, and that even square lattice. And square lattice, as I told you, it gives the magnetic frustration because there is a interaction is such that spin does not know which is. So magnetic geometrical frustration, low dimensional, that is 2D, and also you are dealing with copper, which has spin half. So this kind of system are prone to have quantum fluctuation, zero temperature fluctuation. See, this quantum entanglement in real material, what I am talking about, is possible only when there is a quantum fluctuation, spin fluctuation, and that happens, as you know, at 0 temperature, 0 Kelvin. So 0 Kelvin, this quantum fluctuation has to be so strong that will drive magnetism, quantum magnetism, even at elevated temperature. So this is the physics we are talking about, which is away from the classical mechanics. Yeah, how to get more and more. So this is yet another example that this is called this separation. This is the organic ligand. Separation 13.313 angstrom. How do we know all this? By doing diffraction experiment, we know crystal structure, back diffraction, 2D sin theta. So that means here you see the magnetic layers are well separated, and essentially 3D material you get a layer of this Kagome spins. So these are so that means we move in a trajectory where real life is 3D material wise, crystalline material, but magnetism wise, magnetic material wise, we are low D. We have low spin, we look for copper. We look for this kind of geometry, which is called Kagome geometry, gives spin frustration. So this is the way you have to design a material, you have to visualize a material, and then study the property. Then you see how the quantum property, how much is there, quantum entanglement is there or not, to what extent it is there, and so on. And we use Newton very highly for that. Then I will be only now explaining only one example, because of limited time, that where we have seen the spin quantum entanglement. And so essentially I will be describing the work of this paper. Because of time, only one example. So here I am talking about the spin half trimer chain. Spin half comes from copper 2+. All other are non-magnetic, okay? And they so happen, the building block in terms of the crystal material is 3 spins, trimer. So if you take one trimer, keep adding, then you get chain, and like that there are different chains, you get the entire material, okay? And here, the exchange interaction, magnetic spin Hamiltonian, if you write J1 is the exchange interaction between this, then J3 is this one, these two ends in a trimer, and between two trimers, this exchange is J2. So that is J2 is between 2. So this is the physics. And this kind of tough experiments, we did a lot of experiments in our lab, but we had to also do the inelastic neutron scattering by submitting proposal to UK, and he was the instrument scientist. We also had to see we could do the magnetic field study on this up to 12 Tesla, 120 kilowatt state, down to 1 Kelvin in my lab. But then we had to do magnetic field study, magnetization study up to 59 Tesla we could do. That was in Dresden. And again by submitting proposal, and that gets accepted internationally at the Dresden high magnetic field. That was the requirement for this kind of experiment, to establish that there is quantum entanglement. So you need to understand the difficulty, but then to publish in this kind of journal or to understand the total physics, you cannot simply stop with the experimental results. You have to give theoretical viewpoint. For that we approached Manoranjan Kumar from SN Bose, and he did DMRG calculation. So all these are gone in this particular work. Yeah. So, and this is the actual picture, crystallographic structure of the material which I am talking about. Detailed structure. How do you get? Or by doing Newton diffraction. I will not go details of that. As I just explained, this is one timer, this is interaction J2 between two timers, and this is kind of real structure. And this is what we do, X-ray diffraction. As I told you, this is a crystalline 3D material. This is Newton diffraction, crystalline 3D material. This kind of detailed interaction, detailed structure is this atoms, where are the oxygens, what is the bond length, what is the bond angle, how they are interacting, and they are all super X interactions. If some of you who are in the discipline of magnetism, you know super exchange, interaction, good enough Kanamori rules, good enough who got Nobel Prize and passed recently, and this kind of X interaction you have to understand. You need to know the crystal structure in detail before you go for magnetism. That is what is done by doing detailed diffraction experiment, both by using neutron and X-ray. Yeah. Then we do this magnetization study. As you see, this green curve is only up to 12 Tesla, and that is, as of now in India, 12 or 16 is the highest. We could do that, and it is like a linear. But experimental demand was that we must do very high field measurement, so that is up to 59 Tesla we could do in Dresden, and you could see this. This is the quantum effect, and the solid one is the calculated theoretical base by the DMRG calculations. This is the beautiful experimental demonstration of quantum one-third magnetization plate 2. This cannot be explained by classical physics, by classical mechanics. So one-third magnetization plate 2 is a pure quantum mechanical, and out of this, and I will come to the little details of that. See, how do we explain this? This one-third plate 2. See, we have spin timer, 3 spins of copper half, and you know ground state is spin half and spin SZ could be plus minus half, S equal to 3 by 2 and SZ could be plus minus 3 by 2 plus minus half. And I know under magnetic field, this S half, it is getting splitted like this, S3 by 2 getting splitted like this. This is nothing but Zeeman effect. And when you see, to start with your material is here, so it is at the ground state. Okay, you apply field and it goes to saturation, but here it is the spin half state, but then this jump is from spin half to spin 3 by 2, the next excited state at this field. So at this field there is a crossover from this quantum transition from this ground state to first excited state. Now, when you read quantum mechanics, you have read all those. But in a real life, that is what I am again trying to stress upon, that you have to have a material where you can see this kind of quantum transition. When you talk about quantum properties, quantum entanglement, quantum anything, one has to know which quantum states we are talking about. So these are the quantum states we are talking about. This realization has to come by experimental means. And now we did powerful Newton inelastic scattering, and without going into detail, this is the excited states A, B, C. Experimentally we could see, and theoretically we could, and these are the spinons, doublons and quaterns. And I say that these quantum new composite excited states, this is the very first experimental observation of this new kind of quantum entangled states, and this and after writing the graph, when we were looking for this, one theory paper came, for the first time. This is, this is just they gave the theory and which also follows this phase diagram. So ours is very first experimental realization of the new quantum states, quantum entanglement. Now, little bit, two more slides on this. This, again I said, this quantum, what I say, quantum entangled states. This is my ground state, spin. This is first excited, second excited. But if, when there is a timer interaction is there, J2 is non-zero, and J2, with this kind of strength, it doesn't happen. See, entanglement does not happen for any kind of strength. It has to be less than J2 by J1, that is between trimer and within trimer. The quantum mechanical spin X interactions has to be less than this in order to have this kind of quantum composite excited states and quantum entangled states. These are quantum entangled states. And as I said, this is the very first experimental realization. And there is a strong quantum entanglement. Why I am saying strong? That evidence is here. When you do this Newton inelastic scattering and look at the excited states, right from, see, these are the doublons and quaterns, which I told you. As a function of temperature, this is the real spectra, this is the integrated one. You see these doublet quaterns, they exist almost up to 250 Kelvin, not very far down compared to 300 K room temperature. So this is unbelievable in the sense, as you know, the quantum fluctuation which happens at 0 Kelvin, that quantum fluctuation is so strong that its precursor effect is felt even as high as 250 Kelvin. And here I like to stress upon the fact, if you want to have, let us say, quantum computer which will work at room temperature, then you should have a material which will go here at 300 Kelvin. So we are going towards that. And I must provoke you that following this work, another work we are almost getting ready to submit, where we have seen up to 400 Kelvin, cousin brother of this system. Okay? So this kind of materials are so promising, it is unbelievable that quantum phenomena, this entangled state can have realization very close to room temperature. And before wind up this part, is it that quantum entangled state in a magnetic material we can have only with spins? Can we have with the orbital magnetization? You have the spin magnetization and orbital magnetization. Answer is yes. This is also very, very new area. And without going into details, if there is a spin orbit coupling, let us say you have cobalt 2 plus. This is the theoretical paper. It was shown. And the realization of that. J spin of cobalt plus 3 by 2. So 3 by 2 you reduce to half, and then you get the system, as I said, lowest spin value, this kind of realization. And on that we have worked a lot, as you see, latest paper just submitted and other papers. This is the quantum state out of this orbital entanglement, orbital magnetic entanglement, not spin. So lot of work in this sub area. I will not describe all. So then, this is in the last few slides, I like to touch upon, as I said initially, that why do we have to bother about entanglement? Of course, it is pure quantum mechanics. It is a quantum phenomenon. We need to understand the fundamentals of that. This is textbook knowledge is something, and in real material you have to get the entangled state. It has relevance, and as you know, the National Quantum Mission, it was, announced on April 20th this year by Union Cabinet that 6,365 crore the quantum mission project is sanctioned, and that is what is going on. We are somehow involved in that. So that means the intention of this quantum technology So what we are talking about, the direct relevance in quantum technology, so far what I talk in terms of very fundamental science. Now, what we are doing in BRC physics group, that is the national, that was just announced April 20th this year. But in BRC, as I said, the fundamental physics I started with my research group in the year 2006 with respect to spins. Okay? And you see in BRC physics group in last year, 22, July 22nd, we sanctioned a project for 5 years with 21.25 crores sanctioned by DAE in order to have indigenous scaling technology. This is as far as physics group BRC is concerned, where I come from. This is the design and fabrication of Josephson junction and resonators. See, here only the quantum material will be required. But here Josephson junction means people are not using superconducting materials to make qubits. As I said, qubits you can make by photons, by spins, by superconducting materials, by ions, trapped iron and so on. There are many ways to make qubits, as I told you already. So this is another approach we have taken. Then microwave circuit design, electronics. See, because you have to control these qubits, you have to manipulate the qubits, you have to read the signal, you have to feed the signal. So there are a lot of things. Then you have to do all these things as of now. I was just claiming that we are going to get quantum computer room temperature, but as of now, all are at sub-Kelvin temperatures. We have to have a temperature bath at sub-Kelvin temperature. That also we are building. So finally, we will be getting the quantum computing device using this superconducting platform as per our institute projects. So this is a few view graphs. So far what we have achieved, 3D resonators. You see, this is the 4.3 gigahertz at cryo. This cryogenics, so far it is working. We have made this cryogenics, which is down to 1.04 Kelvin, but we have a project to go to millikelvin, and the cavity, this works this. As I said, why do you need this? To manipulate or read out the qubit state. Qubit has to be entangled with the resonator. Because how do you interact with the quantum qubit? That is what, the interaction process. And these are the designs I am talking about. And see, this is that low temperature, facility which I am saying, at this temperature doing the experiment, testing those. These are the Q factors of the niobium cavity, aluminum at this temperature Q factor. These are the experimental results. As far as this project is concerned, we have achieved. And this is what indigenously we are trying to make this temperature bath while we will be keeping the qubits at 200 millikelvin. So far we have achieved 1.04. We have to go there. This is design and we are working on that. This is also under that project. And as I said, development of control electronics and addressing the qubits. See, BRC is an organization, Professor Grover and Professor Patel, they all know very well that there is a multidisciplinary organization. You can catch hold of right groups, and this is the control electronics to control these qubits. So work is going on, and this particular work we are doing in collaboration with IIT Bombay nanofabrication facility, and this kind of activities. This is the target for this year. As you see, this is in our project way. So with this, I must acknowledge my colleagues, particularly the core part of the work, as per the title of my talk, that quantum entanglement in spin system and probing using neutron. So this is what my close colleagues, this is the theoretical support. We approach Manoranjan, and this is the high field Dresden group. This is the instrument scientist from ISIS-RL, where the inelastic neutron scattering proposal we proposed and got the beam-time and carried experiments. So with this, I thank all of you and the Department of Physics of this university. I'm really grateful. I'm really pleased to be here. Thank you so much. Yeah. Yeah, sure.
It's a very excellent lecture I have heard on quantum entanglement. So thanks a lot for presenting this. I'm not involved in this field. I have a simple question perhaps. I could not get how the interaction is affecting the entanglement. That is one. And second is how did you measure these states, spin-on?
Yes. No, it is DAE only, sorry. Yeah, no. It is our internal project. I said it is, there I meant to say the national mission on quantum, it was declared 20th April this year, whereas we started the, yeah. So one is that, as I go back, how do you measure? Yeah. See, this is how do you measure those quantum, states? This is one of your questions. See, the neutron, it has the neutron beam which you use. It has specific energy, the incident energy which we call EI, and then it interacts with the material. And when a material has this kind of energy levels, this is the spin-on, these are the excited states, and then neutron when it interacts, depending upon the gap, depending upon the gap, so neutron can lose this much energy, or gain this much energy, here it has to lose, and then neutron will be losing this much energy, so system, this band gap, this gap between these two states will be reflected. So this is the way we will measure. Basically inelastic, but through inelastic process using neutron magnetic moment. So neutron with magnetic moment interact with the magnetic states, but in that process it is excitation, so neutron will lose energy. No, in this good question, it is so-called Q dependence, that is 4 pi sin theta upon lambda. Yes, Q dependence is there very weak, but here it is the powder average. In a single crystal data, yes, we do have little Q dependence. So, and then from the Fourier transform, if we do it, then we get this spatial dependent. But on the powder average data, that's why it is looking flat. Yes.
Kelvin region. So, what is the nature of cooling there?
Yeah, it is, see.
Just for information.
Yeah, see, this basically helium, liquid helium, and helium-4 and helium-3. This is the technology. But the question that why do we need to have that kind of temperature? Because otherwise this quantum coherence, what is there?
That will,
when you talk about superconducting material, let us say niobium nitride based, it is TC below 10 K, and then we have to go in order to reduce this, get rid of the effect of decoherence, quantum decoherence, so the superconducting decoherence. So that's why it is preferable to go to as low as around 200 millikelvin. But as I showed the result, the initial result, even at 1.04 Kelvin, we have seen good signal, but that still with noise, that is the difference.
Last, how do you measure it experimentally?
Yeah, experimentally.
I did not get a feeling.
Yeah, experimentally, when in this qubit system, we give the pulse, okay, and then we read it out, because see, it is the, as I said, it is the entangled state. So finally, the pulse what is given, the input and the output it gets entangled with all possible states.
Which is the instrument.
The electronics, that's why the cavity, that's why these resonators are required. Resonator is the interfacing, this is my statement as I said. To manipulate and read out the qubit state, qubit has to be entangled with the resonator. So this is another challenge. That's why we are building all the resonators, which are and they are working at this kind of frequency to get the interaction, to get the reading, and that is the technology. Yes, all very good questions.
You gave an example of sodium, copper, germanium. Do you think that the structure has become such that copper is ionized more than one, therefore copper D cells as the magnetic atom in your system?
Which one you refer to? Copper this?
That is sodium atom, copper. There is no magnetic impurity.
No.
So from where does the magnetism come?
Copper 2+.
It means copper, you press in such a manner that copper gets ionized more than one. Only then it becomes half-filled.
Yes. In fact, we have re-verified experimentally using this EXAPS and the XPS that copper indeed is in 2+. So copper has spin half, and that copper spin half is giving 1 ampere electron, and that is spin half, and 1 Bohr magnet. Yeah.
Okay, that's fine.
And so copper is magnetic.
Yes.
That is it. And in a country like USA, they have centers for the advanced materials. They only create materials, and then they use for their things. I don't know whether they sell or not. I don't know, because they will not sell it. There is very advanced technology to fabricate the material. Is there any center in India?
India greatness. But for the time using reception junction, but what will be using that reception junction technology is known in the sense the bath will be at sub-millikelvin temperature, and that is the one. And the electronics which you all do, everything has to work accordingly. So that is the technological great challenge.
So I think this is the forefront of
Yes.
science these days. Material,
Yes.
that is another area which is a new. I think people should take initiative. I think India should take initiative, private center for the materials.
The plan is that there will be
without
few
materials
hubs.
you cannot do anything.
No.
Because you cannot do anything.
No, there will be few hubs, technology hubs in the country, and we understand the part, and then that is the way it will. But of course, it is a challenging job, and it is better to take this challenge and go forward.
Do we have any questions from the students?
Yes, students, I'll be happy to answer your questions. That could be.
Okay, so I think you can even discuss with him during the tea time.
Sure.
So now I would like to request Professor S.K. Tripathi to please present a vote of thanks, and everybody should stay for a cup of tea after that.
So good afternoon to all. Today I feel honored and privileged to get the opportunity to propose a vote of thanks on this special occasion, 7th Professor B.M. Anand Memorial Lecture, followed by a book launch. I, on behalf of the Physics Department and Professor B.M. Anand family, convey my deep regards and hearty thanks to our Director, Research and Development, Professor Harsh Nayarji, who has spared his valuable time from his busy schedule. My special thanks to our former Vice Chancellor and eminent physicist, Professor Ken Pathakji, for his gracious presence at this event and memories shared with us about Professor B.M. Anandji. At this juncture, I would like to thank our former Vice Chancellor and eminent physicist, Professor Arun Kumar Groverji, for various help and guidance that radiated a source of energy within us we received towards organizing this event. Today we have launched the book entitled Bal Mokand Anand, His Life and Sincere Across the Partition of India, written by Professor Rajinder Singh. Therefore, I want to extend my warm regards and heartiest congratulations to you, sir, for writing such an exceptional book. We hope that in future also we will be benefited. We are honored to have a lecture for the 7th Professor B.M. Anand Memorial Lecture by Professor Yasham Yusuf, Director, Physics Group, Bhabha Atomic Research Center, Mumbai, on revealing spin quantum entanglement by neutrons. We feel enlightened and believe that we got to learn many things from his speech. Words would fall short of describing how much knowledge we could derive from your lecture. I would like to thank our chairperson, Professor R.K. Puriji, for his constant help and guidance to organize this lecture successfully. We work in the department as a family, so I am very much thankful to all our current and former faculty colleagues and non-teaching staff members who always stand by us and motivate us. I feel proud and thank you for making this event a successful one. Once again, thank you to all.